We are going to compare the strengths of these two acidic solutions. And when considering the pH, there's two factors of an acid to think about. One, its concentration, and two, is it strong or weak? These are both weak acids, but one is a lot weaker than the other, as indicated by their acid dissociation constants, or Kas. Now, the acid dissociation constant is just an equilibrium constant for the dissociation in water of that acid, which for phosphoric acid is technically this reaction with water. Remember, the equilibrium constant is products divided by reactants, and we don't include pure liquids or solids, so we usually just ignore the water over here. So what we can gather from the larger Ka value for phosphoric acid is that the dissociated side, our product side, is going to be more favored. There's going to be more hydronium, which is what makes the solution acidic. Oftentimes this hydronium is just written as H+. You might see other Ka values associated with phosphoric acid, such as this one, but this is for the second dissociation of a second H+ off of this acid. And that's not what we're looking at here, so don't worry about this one. Alright, so let's start to get down to it. We're going to need to do an ice table, because since the Ka is an equilibrium constant, we're going to need to find the values of these things at equilibrium. Often when we make an ice table, we'll kind of abbreviate the acid as just the H+ that comes off, and then A, the rest of the acid, and the hydronium is written as H+, and then the conjugate base is often A-. So let's do that with acetic acid. Let's start with our 3 molar acetic acid, do an ice table for it. Alright, here's our setup. For acetic acid, our initial acid is pretty simple, it's just given as 3 molar. Why is this not our equilibrium value? We have to think of it as we're throwing we're throwing enough acetic acid to make 3 molar into some water, and the instant it hits the water, it hasn't dissociated yet. Given a millisecond or so, it will come toward reaching an equilibrium where some of that is dissociated into H+ and A- and some is not. So if we look at H+ here, the initial value is what we have to assume is before any of our acetic acid dissociates. So this would be the H+ concentration in pure water, which is not 0 since water autoionizes. There is always going to be some concentration of H+ and OH- in water. And if it's neutral, it's going to be about 10 to the -7. But this is a very small amount, and we can often assume that it will be a negligible amount compared to what will be there at equilibrium. So for acids that are going to end up below a pH of, 4.5-ish, we can just say this is 0. And for the conjugate base, the acetate, we can definitely say it's 0, because none has dissociated in the first instant. For our change, we have easy stoichiometry, a 1-to-1-to-1 stoichiometric relationship here, a ratio. So whatever we gain of our H+ and A-, we lose of our acetic acid. And for our equilibrium concentrations, we just add initial to the change. And it is these equilibrium values that we are going to look at and do math with. So what do we know about the Ka? For acetic acid, we know the value, but we also know what that equilibrium expression is. It's the products over reactants. This should look pretty familiar to you. And when we put in the values we have in our ice table for equilibrium concentration, we get H plus times A minus over HA. X times X is X squared. And here's a trick. If at all possible, we want to get rid of our lone X on the bottom here. If we don't, we would have an equation with X squared, normal X, and some normal number. In that case, we would have to use the quadratic equation, which can be a bit of a pain. So, in situations where the acid dissociation constant is no bigger than 10 to the negative fourth-ish, we can just assume that this X value would be very small compared to the 3, and that 3 minus X is pretty much the same as just 3. So we can do a kind of approximation and eliminate that X there. Okay, so let's look at our equation. I'm going to just extract the important parts here, like such, and then I'm going to solve for X. And we have ourselves a value. And it just so happens that in our setup here, X is equal to the hydronium concentration. So let's take that value and use it to find pH. Here's our equation for pH. Here's our value of hydronium concentration. And here's the pH of our acetic acid solution. Now to compare it to the phosphoric acid. Now, I'm not going to redo everything. Let's go back and look at the work we've done and see what changes we have to make for phosphoric acid. First, let's address the fact that phosphoric acid is 1 molar here instead of 3. So all our 3's should become 1's. This would be a 1. This becomes a 1. So that side is just X squared. The 3 disappears there. And then the other difference is that the Ka is different for phosphoric acid. So this value should turn into this value. So in this case, our X should just equal the square root of the Ka of phosphoric acid. And that should give us an approximated value of the hydronium ion concentration and pH. Why do I say approximated? Because we did that estimation still where we got rid of this X here. This value, this X would be bigger for phosphoric acid because it has the greater Ka. There's more dissociation, more H+. So because the Ka is greater than 10 to the negative third, we might have a significant error in our values that we got here using that estimation. But I like to live dangerously, so that's alright. But technically, to get an exact value, we should use the quadratic equation and leave that X in there. But qualitatively, I think we've definitely seen that the 1 molar phosphoric acid is more acidic than the 3 molar acetic acid by a difference of a pH unit of about 1, which means, since pH is a logarithmic scale, that there's about 10 times higher concentration of hydronium ion in our phosphoric acid solution.